Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today I would like to talk about one of the gems, one of the jewels of analytic number theory. It's really a cool statement that kind of motivates, well, let's not count. So sometimes it's somewhat better to not be, well, too precise if you want. So this is a very precise statement. It's not about being mathematical precision. It's more about whether you want to nail down something spot on or whether it's okay to nail down something, well, up to some potential error. And sometimes, and that's kind of the idea here, sometimes to nail down something precisely is just terribly difficult. I mean, really, really difficult. But to nail it down essentially precisely is not so bad. And one of the main first examples historically was actually the prime number theorem, which goes back to quite a bit. So something like 200 years, a bit more, we'll see that. But the proof is much more difficult, and it took a while for people to work on the proof. And nowadays we have many proofs of this theorem, and some people actually collect proofs of this theorem. So it's kind of in between being kind of interesting from the point of view of proofs and not too difficult. It's kind of in this nice range of where I can say something. Anyway, so really the point here is that we really don't want to do the count. So sometimes it's better not to count, but only to count in quotation marks. And that's what we are going to do in this video. Well, obviously, that's what the prime number theorem wants us to do. And it's kind of the first example of its kind. And surprise, surprise, the prime number theorem is about prime numbers. That actually is a surprise in some sense, because sometimes the naming in mathematics is kind of very, very strange. Anyway, in this case, it's really about prime numbers. And kind of the point that people know or realized a long, long time ago, it's a little bit hard to nail down, is that prime numbers are quite random objects. Okay, it makes sense to study them. They're kind of the elements of multiplication, like in the periodic table of Fred, so like the elements of multiplication, but they are kind of pretty random in some sense. So here's a nice illustration. So you put the primes on this little spiral that clearly goes through all positive numbers eventually, and you put a dot or a red box or whatever whenever you see a prime. So 1, 2, 3, 4, 5, 6, 7, and so on. Right? So you put a dot for every prime. 1, 2. So here's the first one. 3, 4 is not a prime. 5, 6 is not a prime. 7, and so on. And you do that, and well, okay, it looks like a chessboard or something. I don't know. But if you zoom out a bit, it's absolutely clear, or at least the picture hints that prime numbers are pretty random, because this essentially looks like noise. Like if you just do something random and you just collect the background noise of the universe, you will get a picture that looks very, very similar. So prime numbers are essentially random, or they appear randomly. They're not random themselves. I should have said that clearly. They appear randomly. So they just pop out of the blue, and whether we have found a prime number or not, that's a very different question. But anyway, can we say something about when they pop up? Well, usually, if you just look at this picture and we come back to our idea that we don't want to do the count. Let's say we want to do the count, then this picture is saying that there's essentially no chance to say anything. It's noise. That's what it is. It's noise. There's no way we can say anything if we really want to do the count. So maybe we don't want to do the count, right? And that's what the prime number theorem is all about. So this is a paper by Legendre a long time ago. I wasn't quite able to write it down, to find it down the first instance of this. So Gauss also has something along those lines. But anyway, what people did about, let's say, 200 years ago, it's a bit more, is they had tables of prime numbers. So nowadays, your laptop or your phone probably can spit out the first prime numbers, the prime numbers up to 400,000 in like a blink of an eye. But some time ago, it was quite some work. And what can you see here? So what Legendre wants to do, Legendre, they wanted to count the number of primes, well, up to whatever number you see here, up to 10,000, up to 80,000, whatever, and eventually up to 1,400,000. And they came up with a formula, and that's exactly what the formula gives. So the formula counts whatever, 8,717 primes, up to 900, what is it, 90,000. Okay, and the actual count, so if you really sit down and count primes, which is really difficult, gives this number. Okay, fair enough. By the way, fun fact, at least my Mathematica, I hope that's true, says that there are not 1,230 primes below 10,000, but actually 1,229. So apparently it's really difficult to count primes, right? So you might be off. Computing a formula is much easier. So yeah, counting primes is difficult. Computing a formula is much easier. So having a formula, that's awesome. So people looked for a formula, and here Legendre already had a guess for a formula. And it's not so bad, as you can see. So it is not so far off. Okay, so people looked at those prime tables for a long time, and they realized that there might be some formula, which is not perfect, right? We're not doing the count. That is off by a little bit, but it's also not so bad either. So maybe that's what we should look for. And that's the essence of the prime number theorem, right? You give up the precision, you're not spot on, but you have a formula which is much easier than just sitting down and counting primes. Okay, and the formula, not quite Legendre's formula. Legendre massaged this formula a little bit and added in a constant. But anyway, forget that. The constant won't help you. So in general, so pi n is the number of primes, lower than n, smaller than x in this case. And the formula is a really simple formula. It's just x over log x. And the ratio between them goes essentially to 1. That's what this picture says. I won't comment too much on the other formula. There's an improvement of the formula. It's called the logarithmic integral. And as you can see, the ratio of that one does a bit better. But anyway, so the point is counting primes is difficult, but there is a formula which is not really good in low ranges. As you can see, it's quite off in the low range. But eventually, it will kind of converge nicely to the counting formula, and counting primes is difficult, so the formula here is simple. So that's the point. And this is an asymptotic formula. I will make a precise statement in a second. Yeah, and that's what Legendre and other people did, and it took a while to get proven, but that's essentially the statement. So now I swap to n, because I don't really know who wants to call number of prime numbers x, but anyway. So pi n is the number of primes lower than n, and this is asymptotically the same as n log n. And n log n is, but by the way, it doesn't really matter with what kind of log you take here. Let's take kind of natural log, doesn't matter. But anyway, pi n log n is just a really simple function. It's super simple to compute, while counting primes, well, if your phone does it, I would rather rely on your phone, but if you do it by hand, at least I would miscount a number of primes. And because this asymptotically means they're the same for large n. And this is not saying that we'll see that in a second, that the difference between that goes to 0, but rather the ratio goes to 1. So the ratio here goes to 1. That's saying it's asymptotic. So essentially, you just compute that number and you're in a good range for the counting of primes instead of counting primes. And there's a slightly better version in a certain sense, which is this logarithmic integral, but I also find it more difficult because it contains an integral, so I'm going to ignore it. But it's well known for kind of a long time. And I should remind you here that being asymptotically the same is not that the difference goes to 0. The difference actually gets, as you can see, arbitrarily large for both of them, for the logarithmic integral and our little formula here. And that's really not the point here. The point is that the ratio goes to 0. And actually, those things will swap signs kind of arbitrarily often. So that's not the point. The point is the ratio goes to 0. So you get the order of magnitude right, but there might be still, well, it is still off by a bit sometimes. And that's kind of what Legendre tried to correct here. So Legendre was essentially using the top formula here, but was a bit unhappy because the top formula doesn't give you this spot-on nice result and put it in an extra constant here in the denominator to make it look slightly nicer. The constant won't help you in general. Eventually, it will go off anyway, but that's what Legendre did, and it actually doesn't look so bad. Anyway, so the prime number theorem is really about not doing the count. And well, the upshot is you get something you can prove instead of you have absolutely nothing to say. And the disadvantage is that you only get this asymptotic formula where even the differences get arbitrarily large and you just get somehow the order of magnitude correct, which is still an absolutely fabulous statement. And this kind of triggered, I'm not quite sure whether you really want to call it at the beginning of analytic number theory, but it's certainly a gem in analytic number theory, many ideas of the same type. So sometimes counting is just really difficult. I'm not just talking about number theory anymore. Sometimes counting is just really difficult. A good example would be something like the number of partitions of n. Very difficult to count, but there's a very efficient formula for it, which is not perfect, again, but does a good job. And there's a whole industry in mathematics built on those ideas to not do the count. Anyway, I hope you enjoyed this video, and I also hope to see you next time.